Good morning, everyone, and welcome to the third episode of Steel Motive and our design and engineering process. I'm George Coates, Technical Director with World Auto Steel. We are a global consortium, the automotive arm of the World Steel Association, and we have 18 global automotive steel producers representing some of the largest contributors to the automotive industry in the world. And I'm delighted again to be joined by Neil McGregor, who's the chief engineer with Ricardo. Neil, welcome to the program again
Hi.
today.
Okay, George. Hi.
Yeah, we're doing well this morning, and thanks for joining us middle of your day.
Yep.
So, in our first couple episodes, we kind of gave an introduction to Steel Motive and what was the motivation behind the program, why the steel industry decided it was important to develop this program. And backing up a bit, the steel industry, through this consortium, for about 25 years has developed technical programs, and we've used renowned engineering organizations and institutions such as Ricardo to execute those programs. And every so often, every 6-8 years, we might do what we call a halo or legacy project, which is a full vehicle program, and that's what Steel Motive represents. So that's just a little bit of background as to how we got here. So anyway, we've talked about the introduction, why we did Steel Motive. Then we talked a little bit about the materials, applications, and fabrication processes in the program in our second episode. And today, for the third episode, we want to share with you all the effort and the processes that we use to optimize weight and stiffness in the Steel Motive concepts. So with that, Neil, I'm going to hand it to you, but I just want to prompt by saying we all know that weight's so important for automotive vehicles, right? The weight directly affects the amount of energy required to propel or move the vehicle. Of course, it's a significant contributor to the life cycle emissions for that vehicle. And as we know, it's all too important in crash and safety performance. And so with that, if we can cue up the first slide, and Neil.
So thanks, George. Very good points about the vehicle weight. And I've spent a significant amount of my career devoted to making vehicles lighter. So Steel Motive was a perfect opportunity to apply what I've learned in my career to this really exciting, fantastic program. So on the vehicle weight, what we're seeing on this graph here is looking at the vehicle curb weight, and particular SEM1. This is our smaller vehicle. So on the y-axis here, we've got the vehicle weight. We've got the little dots and marks on there are kind of is data that we've taken, public domain data for current production battery electric vehicles, kind of from A segment all the way up to sort of a larger SUV and F segment. And on the x-axis there is we've got a metric vehicle box volume. So what we do there is we multiply the length times the width times the height of the vehicle, the overall dimensions, and that gives us a meter cubed number. And then when we cross plot those, we tend to get a bit of a trend line. So, there's no great surprise. The larger the vehicle, the heavier the vehicle, and you get kind of a nice trend line. There's some, disparities there, depending on things like the size of the battery. Some vehicles have a larger battery, so they're typically more heavier. The different coloured dots on there, so the grey dots are primarily steel body, steel structure vehicles. They're multi-material vehicles, and the green dots are kind of primarily aluminium vehicles. So those dots on there are all kind of current production battery electric vehicles. And what you see on this diagram is the orange dot there is where Steel Motive SEM1 sits. And you can see for the size and the dimensions of the vehicle, the curb weight of Steel Motive is significantly lower than current production vehicles, 27% lighter, or about 600 kilos lighter than the equivalent present day battery electric vehicle. So that's quite significant, and we put a lot of effort into achieving that weight, and we're pretty pleased with it. And as George says, that has given us, the secondary effects of kind of crash, vehicle efficiency, LCA, cost, and so on. So that in itself is a pretty good result, one that we're particularly proud of. The question that everyone always asks us is, that's great, but how did you achieve that, and why was that achieved? So maybe if you go to the next graph or the next page, George, this essentially answers that question of why is Steel Emotive so much lighter than a present day production battery electric vehicle, and this weight walk kind of shows that. So on the left hand side, say a typical C segment battery electric vehicle comes in around about 2,100 kilograms curb weight. And on the far right hand side, we've got Steel Emotive at 1,512 kilos curb weight. So that's the 600 kilos or 27% weight reduction. And how we walk from those two numbers. So firstly, Steel Emotive is a future hypothetical vehicle. The production date is 2030, 2035, which is when we expect the autonomous systems and autonomous legislation to be mature enough to kind of roll out these vehicles in mass production. So we looked at a future battery technology forecast in terms of energy density, kind of kilowatt hours per kilogram and kilowatt hours per litre. Looking at our roadmap of future technology, we estimated that a 75 kilowatt hour battery of the future would be around about 140 kilos lighter than it would be today. And that's down to improvements or developments in battery cell chemistry, cell technology, and form factor. So we factored in a lighter battery in our future vehicle weight forecast. Secondary, with an autonomous vehicle, there are no driver controls, no interfaces. So systems such as the steering wheel, steering column, the dash, the pedals, all of that is essentially deleted and removed from the vehicle. We don't need any of those systems in the vehicle. So when we looked at a typical C-segment passenger car, we estimated the weight of those to be about 180 kilos. So we could essentially delete 180 kilos of vehicle mass from the vehicle in converting from human operated to autonomous. We had to add a little bit of weight in because there are autonomous technologies and systems such as radars and lidars, the mounting of those. The computational power is a bit more significant. It's quite significant. So we estimated that to be an increase of 45 kilos. So we added in 45 kilos. We then looked at future trends in terms of lightweighting vehicle technologies, and we went through quite an aggressive vehicle weight reduction process. We also looked at the weight spiral effect. So when you reduce the weight of a vehicle, typically you get a secondary effect. You can downsize the size and the weight of the chassis components, for example. So when we looked at that aggressive lightweighting, we were able to achieve 197 kilos of weight reduction. And then we'll see in the following slide when we looked at the weight of the body in white and the body structure, we calculated that the Steel Emotive body structure is about 127 kilos lighter than a typical current production steel body structure. So when you add all of that up, that's where we get to our significant weight reduction compared to a current production vehicle. So it's a combination of looking to the future in terms of future technologies and conversion from a human-operated vehicle to an autonomous vehicle. So a lot to sort of digest there, but I hope that kind of explains how we've got to our kind of pretty competitive weight position for Steel Emotive SEM1 vehicle.
Yeah, no, that's perfect. So then let's translate to the body in white. You did a nice job of laying out curb weight benchmarking. So how about the body in white, the body structure?
Yeah, so a similar graph. So on the y-axis there, we've got body in white weight, and on the x-axis we've got the occupied volume. So this time it's the length of the width and the height of the body in white multiplied to give our meters cubed there. And again, we've plotted data from current production vehicles, battery electric vehicles. So the grey dots are steel body structures, the blue diamonds are multi-material, and the green dots there are pure 100% aluminium body structures. And again, you get a similar trend. Maybe it's not as clear with the regression there, but you can kind of see the larger the body, the heavier the body. And you can see where Steel Emotive sits, SEM1, it sits nicely, quite aggressively within the aluminium body structures there. So it shows that we've done a pretty good job in terms of lightweighting, producing a lightweight, advanced high strength steel body structure. So coming in at 282 kilos there. Couple of caveats, couple of nuances there. Our design, Steel Emotive design, is a concept and it's unpainted, and we're comparing the data on the graph. The reference data is all painted body in white with some NVH padding included in that. So maybe the SEM1, the 282, it may be 5 or 10 kilos heavier than that by the time it gets to production. And again, with it being a concept, when you go through prototyping and pre-production development of body structures, that weight typically only increases as you kind of get to resolving snagging issues and things like that. So yeah, it's 282 is pretty aggressive. Maybe the real life number of that is a little bit higher, but nevertheless, the result shows that with our the tools and the methodology that we've applied, we've achieved a pretty competitive lightweight body structure.
Yeah.
So again, a lot of kind of technical information to take in this live event, but yeah, hopefully that explains it.
Yeah, I think the benchmarking slides are really clear, so appreciate you taking us through that.
Yeah.
I want to remark that for the audience, you can see the body in white, and Neil referenced the size C vehicle as a reference. I think in an earlier program we showed the Golf silhouetted against the SEM1, the primary 4-passenger vehicle, and ours is a little bit taller, a little bit shorter, but certainly the same interior occupancy room, right?
Yeah.
And so as we transition into talking about stiffness, I want to say that I know we gave you several challenges with the vehicle targets and the must-be's, like it must be level 5 autonomy. It must have an open box kind of structure because we wanted people to be able to face one another in their seating positions. And I'm just imagining with some of those constraints that we put on you, they created real challenges for stiffness.
Yeah, that's right. Kind of open, box structures typically are less stiff than kind of a conventional passenger car, just because we, as you can see from this image, we effectively removed the B pillar from the body in white structure, and we put that B pillar into the closures. So that gives us a little bit of a benefit in terms of weight, but we lose a bit on stiffness. Removal of that B pillar takes away some of the contribution of the stiffness. But what we're looking at here on this graph is a summary of the body in white stiffness performance. So we set ourselves a target of 25,000 Newton meters per degree in terms of static torsional stiffness, and these numbers should be sort of fairly familiar with most kind of automotive engineers. That's 25,000 is kind of on the low side. Typically these days, car makers are going up to kind of 50,000 Newton meters per degree. But you've got to remember the application of this vehicle is that it's mobility as a service, ride hailing, ride sharing, a taxi. So, and we're not into sort of vehicle dynamics. It's not, it doesn't have to be stiff to kind of go around corners and ride shake and things like that. So 25,000 we felt was a fairly sensible number for the static stiffness. But nevertheless, you can see from the numbers there that we surpassed that target quite considerably. So the body in white alone, 34,000 Newton meters. And then when we run with the trim body, so the contribution from the battery frame and the cover and the subframes, that increases significantly to 63,000. So a very high number, and that gives us, as well as stiffness, it gives us very good quality, body in white quality. So things like squeak and rattle. So when you open the doors, they open properly and they don't rattle and shake and things like that. So a very good performance. And some may say that's why is it way above the target? Probably the reason behind it is the body is mainly the main drivers for the body structure are crash and the crash results. There's a lot of structure and material in there for crash performance, and the stiffness is kind of a secondary kind of product of having that structure in there. So we did take efforts to kind of to try to get as close to the target and as we could, but it's mainly high because of the high amount of material for crash.
Yeah. I see you've got the graph on the right, the lightweight design coefficient. I don't see that used a lot here in the States. Is that common or popular in your benchmarking work in Europe, for example?
Yeah, it's again, this is another bit of a technical one to describe. So the lightweight design coefficient is, quite more generally a European metric that's used in kind of reporting out of body structures and technical conferences and papers. And what the lightweight design coefficient is, it's a measure of the weight efficiency, the structural efficiency of the body in white. So there's a formula behind it. So you take the weight of the body in white and you divide that by the footprint, so the size of the body, multiplied by the torsional stiffness. So what we're aiming for is a low number, so low weight. And then if you divide that by a high footprint and a high torsional stiffness, you get a very low number. It's a really nice way of kind of capturing body in white weight, body in white size, and body in white stiffness. It's a really nice way of kind of sort of bringing that down or boiling that down to a single number. So what we're showing on the graph on the right hand side is, Steel-O-Motive achieves a lightweight design coefficient of just below 2.0, which is pretty good. And then what we've plotted against that is some other reference data from technical papers and journals of current production vehicles, where we can get that data just to show how Steel-O-Motive is, the very good mass performance that we got, the very good stiffness performance that we got combines to give us a very good lightweight design coefficient. So again, we're pretty proud of that number.
Yeah, thank you. Thanks for that explanation. Okay, so this is an interesting graph. Can you take us through the design and engineering process?
Yeah, again, we show this good performance, and then people often ask, because that's great, but kind of how did you achieve it? So this graph or this diagram, it sort of tries to show the evolution, the development of that body in white structure. So remember, the specification for Steel-O-Motive was a clean sheet design, no existing structure for a fully autonomous battery electric vehicle. That's the design brief. So there's quite a lot of new design freedoms. There's no requirement for vision or obscuration. So we can put structure where we would typically put glazing, glazed areas. So what we did is we started with one of these FEA 3D topology load path optimizations. They're pretty common and used fairly widespread in engineering these days. But for us, we had to think about that a little bit differently. We had to change the boundary conditions and the constraints for that simulation quite a bit to capture the subtle differences of autonomous vehicles. So we ran this topology optimization that essentially tells you where to put the material. Remember, lightweight structures is all about the right material in the right place. So that told us essentially where to put the structure, where the key load paths are for things like front crash, side crash, stiffness, NVH. We then go through a bit of an interpretation process to kind of try and understand what that optimization is telling us. We move to a one-dimensional beam model. We then move from the one-dimensional beam model to two-dimensional sectional FEA beam simulations, and then we go through a process of optimizing those beam section profiles and those joint stiffnesses. And then we move to the kind of the image on the bottom right, where it's starting to resemble something more like a body in white structure, where we turn to 3D shell elements and start to increase the complexity of the simulation, start to run more complex simulations, and then go from the bottom right down across to the bottom left image, which is our final design. And that's going through a lot more of the more conventional FEA, CAE optimization loops, optimizing grade, gauge, joint stiffness, and joining parameters. So that kind of summarizes, the process from start to finish, which was essentially sort of 2.5 years of work, essentially to deliver as our lightweight body in white structure.
Yeah, so for the audience's benefit, if we started at the top left, topology optimization, and moved to the bottom right, your first kind of rendering of the body in white, right? Body structure. About how much time elapses there? What's that timeline?
Yeah, probably took us about 2 to 3 months, something like that. And yeah, because it was, we could typically do it a little bit quicker. We had to, again, because it's an autonomous vehicle, we had lots of different design freedoms, and we ran a few more sensitivity studies around, putting structure through the glazing, changing the configuration of the battery, how much the battery contributes. But yeah, that was around about 3 months, to go from those stages.
Okay. So then the heavy lifting really occurs from that 2D view all the way to the final body in white. That timeline would be about?
Yeah, about 18 months or 2 years, something like that. And that's like the heavy lifting, like you say, which is all of the FEA iterations, the optimization. We've got these 64, or we had the great 64 advanced high strength steels to tune from, and then all the gauge thicknesses as well. So a lot of potential, but that means there's quite a lot of optimization loops to go through to get that good result at the end.
And then let's just show one illustration, and then I think we're about out of time. Okay.
Yeah. So what we're trying to do here is just show, drill into some of the detail about how we achieve that stiffness. And this image is showing, a lot of work went into optimizing the sections of the main sections of the body in white structure. So you can see the image there on the bottom right. That's the base of the A pillar. A lot of work went into sort of fine tuning the profile of that, the joining of that, the position of the spot welds, adding in kind of gusset features into the corners just to put the material where it's needed, really, and using and optimizing the right grades of steel and the right thicknesses of steel in there. But that's just one example. There's the engineering report that's freely available to anyone. Goes into a lot more detail about the section profiles and how we exactly achieved the good stiffness and weight result.
Okay, great. And then you just got a quick illustration on joining. If you could take us through that.
Yeah, I mean the joining of a body in white structure really does significantly influence the overall performance. And again, a significant amount of effort went into optimizing the way that the body in white was joined. We, for a high volume production body in white fabricated steel structure, we went with the remote resistance spot welding route. So typically around about 4,000 spot welds in the body in white. We use a combination of 2-sheet, 3-sheet, 4-sheet welding. Some of those, the 4-sheet is really pushing the boundaries, the limits of joining technology. We're pretty confident. We looked and investigated those 4-sheet welding in a lot of detail, and we concluded that they were, they were feasible for high volume productions. Other things to note on the welding, you can see the laser welding around the base of the body in white. That's there for sealing of the battery. You'll see in other events we talk about the battery being coverless, so the modules are kind of neighbouring into the body in white. So that laser weld has to act as the seal between the battery and the body in white cabin. And you see, relatively low amount of structural adhesive used. We only used about 8 meters. Present day production vehicles could be anywhere sort of 80, 100 meters of adhesive. And the reason for that, we didn't need it. We showed that you could see we achieved the stiffness results quite comfortably. NVH was okay. The crash and durability was okay. So we didn't need that much adhesive. Albeit, like I said earlier, this is a concept. Who's to say that you go to prototype, advanced production, that adhesive may increase as you come across more kind of production or quality issues. But for our concept, we used a relatively minimum amount of adhesive. A lot more could be said about the joining. We've only got time to kind of summarize it on one slide, but again, there's more information that can be found in the engineering report.
Yeah, and that is downloadable through the World Auto Steel website, worldautosteel.org. So
Yep.
encourage people to take a look at that. Well, we're out of time, Neil. This is great. Thank you for the detailed explanations of the efforts we took to manage and mitigate both weight and to steel for that open box structure yield a really solid stiffness performance. So thanks for that. We look forward to regaining this audience in episode 4.
All right. Thank you.
Thanks, everyone.
Bye-bye.